Project PhoG develops a unique device for generation of quantum states of light. Quantum light is tailored light with curious properties. Normal light from the sun or a light bulb is full of noise. We can see it clearly in the record of the electronic signal. Quantum light, like that from a laser, is particularly quiet with reduced noise. We can select the type of noise to reduce. The difference between normal and quantum light can be illustrated by an orchestra. Normal light is like an orchestra tuning their instruments. Quantum light is like an orchestra playing a symphony. The individual instruments represent the particles of light called photons, which are bundles of light energy. There are different styles of music which the orchestra can play. And there are different types of quantum light which we can create by choosing how we order the photons. The simplest quiet light comes from a laser. Here the photons are ordered in the same way as raisins in a fruit cake or cars on the road or falling raindrops. This is the most common type of randomness called a Poisson distribution, and it appears everywhere in the world. In the special quantum types of light, this random distribution is designed, manipulated and applied. There are many applications for a quantum light with a very narrow distribution. Such light will be strictly ordered, and we will know exactly how many photon bundles of energy it contains. Such light contains very little noise. Different applications can take advantage of different designs of quantum light. An exciting application area is emerging in quantum technologies. Quiet quantum light is needed for quantum communications, where it can be exploited to securely encrypt messages which cannot be deciphered by even the most powerful supercomputer. Recently, it has even been possible to transmit quantum light from a satellite to Earth. And a video call between China and Austria was encrypted with the help of quantum light. A quantum computer seemed to belong to pure science fiction until even quite recently, but now established tech companies like IBM and Google race to create useful quantum processors. The branch of quantum technologies most ripe for commercial use is quantum metrology. Quiet quantum light is used for high-precision measurements in a range of areas and helps us to create microscopes and cameras with super resolution. The PhoG project builds on work recently completed with the accomplished EU project SuperTwin, which focused on this super-resolution microscopy. The experts from that project, in the groups of Dmitry Mogilevtsev and Dmitry Boyko, continue to work within the PhoG project. Our quantum source of light, which we call a photon gun, or PhoG for short, can create quiet quantum light for all these different applications. This wide performance is enabled by the unique physical mechanism behind the PhoG. History knows many examples of when a foe has been turned into a friend. For example, we usually think of mold as being an enemy which ruins the food in our fridge. But under the right circumstances, it can be used to create cheese or even medicine. How does PhoG work? In PhoG, we need to route light through a channel. In this process, we can reorder and restructure the random distribution of the light in designed fashion. This creates the desired music of light. To channel the light, we use an effect which we are all familiar with from a straw in a glass of water. air and water have different abilities to guide light, which we call the refractive index. This difference in refractive index is used to create channels which guide light along a desired path. We call these waveguides. PhoG is an integrated optical device. A laser is used to write waveguides in a type of glass with special, non-linear properties. This approach can create arbitrary patterns of waveguides to create any designed configuration. The PhoG device itself is a very small glass chip. This allows PhoG to be used in many applications of modern technology. Our light follows the waveguide in glass like water is channeled through a pipe. You can imagine that a quantum network is like a complicated water guiding system. In optical waveguides, we always have an enemy. Light always leaks out and is lost to the system. Leakage will usually destroy the strange and useful properties of our light, but it also allows the waveguides to see each other. In a water guiding system, leaking water can be bad. A burst pipe is a harmful and expensive leak, but we know that a water stream can be controlled and harnessed like in a hydroelectric station or a water wheel. Can we harness the light leakage in our waveguides? By controlling the light leakage, PhoG can turn this enemy into a friend. The PhoG project does leakage engineering in a unique way. This method was developed in collaboration between the groups of Dmitry Mogilevtsev, National Academy of Sciences of Belarus in Minsk, and Natalia Korolkova, University of St. Andrews in the UK. It was implemented in an experiment for the first time by the group of Robert Thomson, Heriot-Watt University in Edinburgh, UK. In design and characterization of the PhoG device, we are actively supported by the experts from the group of Christine Silberhorn, University of Paderborn in Germany. The transfer of these research ideas to technological solutions is led by a non-profit private research company, CSAM, and the group of Dmitry Boyko. The group of Robert Thomson creates ideal conditions for design and inscription of various types of PhoG device using the most up-to-date and cutting-edge achievements in unique laser inscription of the 3D waveguide structures. The size of individual waveguides varies between 18 and 25 micrometers. These are the ultra-thin filiform channels for light and are about 10 times thinner than a human hair. The simplest version of PhoG involves two signal waveguides. Laser light is injected into these two channels. The signal waveguides see each other by a specially woven network of waveguides, which helps to implement our friendly light leakage. By controlling the pattern of the waveguide network, we can control and tune the types of leakage which the light experiences. In the first place, we apply PhoG to super-resolution microscopy on the technological platform of CSAM. Laser light passing through the quantum network of PhoG is transformed into special entangled states of light. Photons pairwise are turned into identical twins of each other. Using these photon twins, we can enhance the image quality. We can make a device more complicated by weaving together several PhoGs, and so generate many exciting types of quiet quantum light. Such a device could be used for modeling of large and highly complex quantum systems, and these models can even be applied to biology or economics. Another basic PhoG device, capable of creating an extremely ordered light with very narrow distribution of photons, will be tested at CSAM for application in a commercial atomic clock which is used on satellites. PhoG will allow us to enhance the frequency stability of the clock several times. Until even quite recently, quantum physics and quantum optics seemed to represent merely a collection of unusual and even mystical phenomena which go against common sense. These days, quantum physics has turned into a science which is at the forefront of real technological advances. These developments were pioneered by the laser, a quantum device which has since reached all areas of human activity. Today, we live in the era of many new achievements in quantum physics, with new applications discovered every day. The project PhoG delivers its own contribution to this process. This is the era of quantum technology.